So I didn't realize this. I actually already had the Excel sheet ready to go. I had done it previously. I'd forgotten I had done it. So what I've done is I've readjusted the data that you guys collected, but I've put it so that the x's do go from 0 to 1 to 2 to 3, as opposed to those jumps. So in other words, previously, the consistent was the distance, 0, 25, 50, 75, 100. What I've done is I've reshuffled the data, so now the consistent is in the time passed. Notice how the distances are no longer consistent? That's because I'm speeding up, I'm covering more distance per second. Is it with me so far? Believing this is fair? Notice this is negative 0.4, which is the model's prediction, right? The model predicted negative 0.37, which rounds to 0.4. So what we can now do is, we can look at those first and second differences we were talking about over there. So let's do that. And this is the beauty of Excel. So what I'm going to do is, I'm going to do equals that guy minus that guy. So that first difference is 3.9, and then using Excel we can drag this down. And those are those first differences right there, 3.9, 7.2, 10.6, and so forth and so on and so forth and so on. Fair enough? Okay, now the second differences are going to be equals this guy minus that guy. And then we'll drag this guy down. And that's what's so cool, is that it's not perfect. Who's saying what? I love that. It's not, if you increase the decimal on it, it's not perfect. Let me do that real quick. Decrease decimal. Oh hell, it's coming out perfect. It's perfect. It's perfect enough. It's perfect enough. The idea though is that that data is so classically quadratic that you end up getting these differences. It almost fits to a T, and that's the beauty. That's the beauty of your model. I mean, the reason it's coming out so perfect is because we're using the model fit, which is a perfect quadratic, if you will, but the data fits the model almost perfectly. So there's really no argument between the data and the model because they fit perfectly. So that's why you can use this to decide whether or not a model is going to fit well by just checking those second differences in your data itself. You can check it in your data itself. Now the trick with that is, and this is a trick, if you go back to your data, which is over here, you can do your second differences off of these, but it's going to be very boring because the difference is 25, 25, 25, 25. The second difference is 0, 0, 0, 0. Well, that's not right because your data is not going up by 1 each time here, right? You have to make sure that your x is increasing the same rate and check the y against that. That's where Excel kind of comes in handy. So knowing that it fits so well, there's your second difference as being, you know, what? I love that. What? What just happened? But what happened is the mathematics of the fit of the curve. An exponential, even if we didn't get that error that we did last time, it wouldn't fit that well. It wouldn't show that kind of perfect fit. And we'll see why next week. We'll see why next week. All right, beautiful. Turn Excel off. Boop. All right, now knowing this, let's do a couple things. Let's do a couple things. First of all, Chad, right before break, you all thought you go, so you're going 19.4 feet per second? I think that's what number you got for him.
Yep.
So Chad came up to me at the break, awesome question. He's like, I think I know how fast you were going when you crossed 200 feet. And Chad, explain your logic.
Okay, well I did 200 feet, but 10.3 seconds.
So he did the total distance over the total time for the whole trip, yes?
Yep.
So this is for, I'm going to make a markup here, for the whole trip. Are you guys okay defining what I did as the whole trip? It's fair, whole trip, yeah. So the whole trip, total distance over total time, that was 200 feet over that 10.3 seconds, which ends up being 19.4 feet per second. Good. Now, that's not how fast I was going when I crossed the 200-foot marker. That's how much I averaged for the whole trip. Just real quick, I'll do a quick Google calculation. We'll teach you guys how to do this too in your next project. The math behind that and also the fact that Google can do it for you. 19.4 feet per second in miles per hour. 13.2 miles per hour. 13.2 miles per hour. Now, is that how fast I was going when I crossed the 200-foot marker? No. That's how much I averaged over the whole trip. Now, people look at me like, the hell are you talking about? That doesn't make any sense. Good. That doesn't make any sense. If I want to know how fast I was going when I crossed the 200-foot marker, my average speed for the whole trip is irrelevant. Right? That's why you're looking at me like that, because it's apple orange. We're comparing an apple to an orange. If I want to know my speed at 200 feet, the average speed for the whole trip tells me something. It just doesn't answer that question. So the question I have for you now is, before we go anymore, this is my average speed for the whole trip. Average rate. Can I use AROC? Just realize that AROC is average speed in this case. It's speed of my distance over time. Average rate of change for the whole trip. Now, what I want to know right now is, what does that mean mathematically? What does the average rate of change for the whole trip mean mathematically? Okay, well, let's figure it out. If it's okay with you guys. It means something. I want to make sure you guys understand what it means, yes? Hopefully, maybe you don't care. Hopefully you care a little bit. So, let's come up here. Yeah, let me erase this. And if you will, go ahead and slap your graph back up. You can turn your scatter plot off if you want to. We don't really need our data anymore. Because the equation is all we're going to be using now, essentially. I mean, if you think about it, that's all we're going to be using is we have that model that's now graphed, and that's going to be that's what we're talking about, my distance that I covered. So I'm going to turn off that 200. We don't need him anymore either. And one real quick way, I think I explained this in that booklet I gave you, a quick way to turn plot 1 off. You see how it's highlighted right there? You can just put your blinker on top of it and press enter, and now it'll be gone. It'll be gone now, so that's kind of nice. And there's my position. Covering more distance over time. So here I am at the start. Here I am at 0, 0, 0 feet, 0 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.3. Here I am at the end. 200 feet at 10.3 seconds. Okay? How does that 19.4 play into this picture? How does that it does play into this picture, but how does it play in? I want to let this question sink in. Thank you guys. I want to hear from you guys in a minute. I want this to sink in. Where does that 19.4 play into this picture? I'll give you a hint. It doesn't play into, it plays into a figure you have to add to the picture. It itself doesn't sit on that graph. There's another graph you'd have to draw. A familiar graph, perhaps from last week, that you'd have to draw. From 0, 0 to 10, 3, 200. What is that 19? What is that 19? Let me see hands. I'm seeing some nods now. We're starting to sink in a little bit. Good, we're starting to sink. Alicia, what's on your mind?
Well, that would be that.
Say it.
Average.
Yes.
Add to what you would find out what the slope would be.
Good. I heard the word slope. Ian, what's she talking about? Yes. If you were to take. Now, remember, this is not how I traveled. But if you were to draw a straight line from 0, 0 to 10, 3, what's 19.4? The slope of that line. Oh, God. Sorry, Taryn. She's like, I should have stayed in bed this morning. I didn't need to hear this. That's how fast I was going on average through the whole trip. Now, you see, Joanne's like, okay, he's yelling again. Now, you got to see why this does tell you something. This is like my friends on the Jersey Turnpike. They covered 120 miles in 2 hours. That means they averaged 60 miles an hour, yes? But remember what they did? They went 110, stopped for a smoke break, got stuck in traffic, went 75, went 40. They were very rarely going 60 miles an hour, but they averaged 60 miles an hour. That's the difference between an average and an actual. When you sum up the actuals and divide them by how many there are, that's the average. So the assumption, you can see why this is kind of silly. The assumption is that I left 0, 0 traveling at 19.4 miles an hour. Or excuse me, 19.4 feet per second. And if I continued traveling 19.4 feet per second the entire trip, I would hit 200 feet 10.3 seconds later. I think that's the calculation Chad did for us. By taking 200, he took 200 and divided it by 10.3. What that essentially did was tell me per every 1 second how many feet do I have to travel every 1 second to get to 200 feet in 10.3 of them? So in other words, every 1 second, I pick up 19.4 feet. 1 second, 19.4 feet. 1 second, 19, and so I'm getting at here, friends? All these little tiny similar triangles in here? You know, if you get tired of that, you can go 2 seconds, but then you pick up, if you go 2 seconds, on average, I pick up 38.8 feet, yes? Double 19.4. If I go 3 seconds, well, I'm out of seconds now. If I go 3 seconds, I would pick up whatever 3 times 19.4 is, yes? So you see what that is? Whatever it is, sure, I trust your math. I'm going to call it 60, a little less than 60. 58.2, is that what you said? See, now the math geek's kicking in. Okay, good. So, now you see how this doesn't answer the question, though. My question was not how fast did I average over the trip. It's how fast was I going at 200 feet. So the problem is this. Now, here's what's really cool about this graph, though. The reason I like starting with it, thank you, Chad, for bringing it up. The reason I like starting with it is you can see that at some places the speed is being overestimated, and at some places the speed is being underestimated and overestimated. See, right now, this is my speed. Well, what was my speed at the very start of the trip? It was 0. I was sitting still next to Pete. Then I said, go, and then I went. So obviously, my speed was 0 at the start of the trip. Clearly, my speed at the end of the trip would have to be more than 19.4 feet per second to make it average 19.4 feet per second. Good. Carrie, what's on your mind right now?
I'm just feeling.
Oh, you're just tracking. Okay, just tracking. Good. Excellent. Makes me happy. Makes me happy. Sorry, I'm like an amphibian. I sense motion. Okay? So can I ask a second question? Let's do this. Suppose we change the frame of reference a smidge. So here's 0, 0 to 10.3. You know what? I shouldn't have done that. Let me leave that on there. Let me use a different color. Blue. Oh, sorry, here. Not there. What's my average speed from here to the end of the trip? What's my average speed from there to the end of the trip? Well, first of all, give me a gut feeling. More or less than my average speed for the whole trip?
More.
So tell me why it's more. Okay, I gotta vote for steeper slope.
You don't have a 0.
Oh, very nice. Very nice. So roughly, what I've done, I love what you just said. Tell me your name one more time.
Faith.
Faith, thank you. You see what I've done is essentially I've gone half of the time. Half, roughly. I'm calling this 5, which is not exactly half of 10.3, it's a little less, but it's ish, half, right? If it were linear, that means I also would have covered half the distance. Because that's what linear means. Time and distance are directly one-to-one proportional. Good. Rodolfo's saying, yeah, but look, you covered a lot more distance in the back half than you did in the front half, yes? So clearly, on roughly the same amount of time, or half the amount of time, I covered more than half of the distance. So logically, because of the larger slope, I've got, obviously, a much larger speed. Now the question is, how much larger? Well, what do we have to know in order to figure this out?
The Y value.
Thank you. And how do we find the Y value? How do we find the Y value at that way? I didn't go over my hands. How do we find the Y value, friends? I think we can do it the same way we did before, yes? But it's even easier because now we have an X value. Use your table. This is where your table comes in, yes? So go to second graph. You have the X value of 5. Just type in 5. Press enter. I get 52.5 feet. Check that out. 52.5 feet. That means I covered only a quarter of the distance to 200 feet-ish. I'm rounding now. I only covered a quarter of the distance in half the time, which means in the back half of the trip, I covered the remaining 3/4 of the distance in the same time. So clearly, my speed, I'm guessing, should be, if you will, about much, much higher because of the slope being steeper. Now the question is, suppose we need some precision to that estimate. Well, can we calculate the average speed between this point and this point now? And I'd like you guys to do it right now. Yes, please, if you would. Please, thank you. Just take some time. Do a similar calculation over here. I'll get you started, and then I'll have you guys finish the calculation.